Okay, so in this lecture, we're going to start to look at the chemistry of carboxylic acids. And we're going to focus not on the derivatives at the start, but just on carboxylic acids themselves. So, as the name implies, these things are acidic. Okay, which means if we treat them with a base, we can kind of predict what's going to happen. If we look at a just bare bones carboxylic acid and we let that react with some base, the negative charge in the base is going to remove the acidic hydrogen to give rise to the conjugate base of a carboxylic acid. Now, it turns out that this is called a carboxylate ion, and it's stabilized by two dominant resonance structures that are degenerate. Remember, in resonance structures, we can't move nuclei. So these two structures are different depictions of the same molecule. What it teaches us is that both of these structures teach us that the molecule has negative charge character, and both of the oxygens of, again, that name was the carboxylate ion. Okay, now that's an important term to kind of take with us. This is sort of a new functional group. It's just the deprotonated carboxylic acid. In some respects, this thing is more important than the carboxylic acid itself. Now, the carboxylate is stabilized by resonance. And in fact, both of those structures are degenerate or of the same energy. And they are also the best contributing resonance structures. So, exciting stuff for the carboxylate. And in fact, a better way of because because the oxygens have such strong resonance character, a better depiction of a carboxylic acid for what it's worth, it would be if we had the R, we're going to attach this to two O's, and instead of having the negative charge localized at one position, it's going to be kind of spread out between the two oxygens. And the H plus is sort of sitting in between these two oxygens. This is especially true if we're in some sort of solution state, which in many of these carboxylic acids are in the liquid state. So this is kind of what we see. Okay, so that's fun. Let's ask the question, how acidic? So let's remind ourselves that the pKa of H2O is 14. Well, it's really like about 15 and some change, 15.7. But if you want to think about it as, 14, that's fine. Well, it's not really fine. But anyway, so the pKa of water is about 15. pKa of alcohol is about 15 to 18, depending on what's attached to the alcohol. You could drop that down too. And just as a benchmark, ethanol is about 15. Okay, so now recall that lower pKa means more acidic. And I guess that's whatever. Okay, the lower pKa means more acidic, so we would expect the carboxylic acid to be lower than all of these. But the reason why I brought these up, as opposed to looking at acids like HCl, is all of these things have OH groups. Okay, so since or because the conjugate base is stabilized by resonance, because it's stabilized, then we'll just remind ourselves by resonance, the corresponding acid is more acidic. Okay, so I just presented you some numbers, and now I presented you some presented you some numbers, and then I presented you some facts. So in general, the pKa of acetic acid is 4.7. Okay. So the pKa of acetic acid is 4.7. That's a really good benchmark. So it's a great benchmark for an acid. So that's acetic acid, and acetic acid is this structure. So it's our carboxylic acid core with just a CH3 group attached to it. So you can see that's a really good starting place for us to think about the pKa of carboxylic acids. If you add some substituents, the pKa will change. And it turns out, interestingly, it will go in either direction. In either direction. That is, if we add like an alkyl chain, so instead of a methyl group, we have a propyl group off the chain. So this would be butanoic acid or butyric acid. The pKa for this is about 5. So my point is it went up a little bit from acetic acid by adding our alkyl group to it. So alkyl groups are good electron donating groups, we now know from our aromaticity section. So we can increase it by adding some electron donating groups. What happens if we add electron withdrawing groups? Well, it goes down, as you would expect. So adding electronegative atoms, and as we know from the aromaticity section, these are inductively electron withdrawing groups. If we do this, the pKa of the carboxylic acid will decrease. And if it decreases, the carboxylic acid becomes more acidic. Okay, so let's look at an example of this. If we take our same butanoic acid that had a pKa of approximately 5.0, and let's just go ahead and add a chloro group to it. So if we add a chloro group, all of a sudden that pKa of 5.0 drops to 2.84. Now this is a pretty big change in terms of acidity because this is a log scale. So we've dramatically decreased the pKa and increased the acidity just by adding a chlorine atom otherwise to the exact same framework. And that's because the chlorine atom is electronegative. Now the reason why, so why did the pKa go down, is the chloro group, or the chlorine atom, is electronegative. It's electronegative, and it stabilizes the negative charge on the conjugate base. So that's what's going on here, is by adding an electron withdrawing group, like an electronegative atom, for example, we stabilize the negative charge. Now, how is the negative, that leads us to another question. How is the negative charge stabilized by electronegative atoms or electron withdrawing groups? Well, what this does is the electronegative atoms / groups will sort of stabilize the negative charge by delocalizing the charge through inductive effects. It kind of pulls on all of the electrons and polarizes all the bonds subtly, even further away from the atom that it's directly bonded to. So the chlorine is going to kind of tug all of the electrons towards itself. Remember, that's the definition of electronegativity. It's an atom that, when bonded covalently, will polarize bonds or pull bonds, the electron cloud, so that it's closer to that atom. Well, when you do that, you actually pull some electron density away from the center that has that negative charge, and that's a stabilizing effect. Minimize some electron-electron repulsion by sort of pulling the negative, some electron density away from that negative charge. So it's a good thing. The negative charge is happier. Well, if the negative charge is happier, or more stable, the acid is more acidic. Remember, when an acid wants to be an acid, it's thinking about whether or not it wants to give up a proton. So what it's going to do is look at the situation and say, hey, if I give up this proton, what kind of situation am I going to be in? Am I going to be in a good situation or a bad situation? It turns out that if you add electron withdrawing groups and you stabilize that negative charge, it's not going to be in such a bad situation. So it's happier to give up its proton. Okay, so the influence of electronegative atoms is distance dependent, or distance dependent, I should say. And so what that means is, well, let's look at some examples here. What that means is, as we move the electronegative atoms away from the carboxylic acid, the acid becomes less acidic. That is to say, the pKa is going to go up. Okay, so let's look at some examples of that now. So we had I'm just going to get these examples while you all are writing down. We had these in front of us, so that's a pKa of approximately 5.0, and that sort of sets the baseline. If we put our chlorine atom at the alpha position on that carboxylic acid, the pKa drops to 2.84. That doesn't really need to be approximated. That's precise enough for me. Now, I chose this example because we can actually move the chlorine down the chain and actually see what happens to the pKa. So if you move this chlorine atom from the alpha position to the beta position, the pKa increases to 4.06. Now we're getting in the realm of acetic acid, and we're getting a pKa unit away from just the parent carboxylic acid itself. And if we move that chlorine atom one more position down to the gamma position, the pKa increases further, thereby becoming less acidic at 4.52. You can still see the difference between this, what it would be is a 4-chlorobutanoic acid. We can still see the difference in the pKa compared to the butanoic acid parent, some difference, but the difference is becoming much more subtle as that effect of the chlorine atom, its stabilizing effect, is dropping off the further away it gets from that center that's going to become negatively charged when we deprotonate the carboxylic acid. So closer to the carboxylic acid means more acidic. Now, in addition to that, more electronegative atoms or more electron withdrawing groups will, think about it, if we add more chlorine atoms or more things that will withdraw electron density away from that negatively charged center, we're going to also make the carboxylic acid more acidic. And again, this isn't quant. We can remind ourselves what we expect to see here. Okay, so let's look at a nice example of that is if we have 3 fluorine atoms, fluorine our highly electronegative element on the periodic table. This is called trifluoroacetic acid. And, you know, acetic acid by itself, like just neat acetic acid, not diluted in water, which is what you typically get with vinegar, is dangerous to use, but for different reasons than what you would expect. Glacial acetic acid is what it's called when acetic acid is by itself. You don't have to worry about like an acid burn like you would with phosphoric acid. In fact, it's more likely to be problematic as just a flammable agent. So it should be stored as a flammable, not stored with acids and that sort of thing, for a safety moment, I guess, of the day. But it also, if you get it on your skin, it can cause organ failure in its neat form, not diluted, that sort of thing. So you want to be kind of careful with it, but not for the reasons we typically need to be careful with carboxylic acid or acids themselves, strong acids like HCl, phosphoric, nitric, all those things can burn us. Sulfuric acid, definitely so. Trifluoroacetic acid, though, has changed the game a little bit. The pKa of this thing is 0.23 due to all of the halogen atoms that are stabilizing the negative charge. This is a highly acidic molecule. And as a result, it's because the pKa is less than 1, this is classified as a strong acid. Should make those notes clear. This is considered to be a strong acid, and so we can, I'll just say this, it's hazardous because it's a strong acid. I think that's kind of interesting, just, you know, affixing the word acid doesn't necessarily mean we have something that's strong and dangerous as because of its ability to donate protons. But we can make them that way in the case of carboxylic acids by adding all these groups. Now, what's cool about trifluoroacetic acid, and the reason why I really like it, is that it can be made anhydrous. A lot of times it's hard to do acid reactions in an organic chemistry setting because we want to use anhydrous conditions without water, because otherwise things will start to decompose on us. Obviously, we could just become better chemists and try to figure out how to do things in nature's solvent. An alternative would be is to use a strong acid that doesn't necessarily need water. Okay, so we've talked a lot about how carboxylic acids are willing to give up a proton, and that's important because they can react with bases to kind of do things. But let's look at what happens if we actually do some reactions with some real bases. Okay, so carboxylic acids react with amines. So amines are our things where we have some, like 3 things attached to nitrogen. Those 3 things could be carbon or hydrogen. There's no carbonyls directly attached to nitrogen. There are no double bonds between nitrogen and another carbon. That would be an imine or a Schiff base. Okay. Excuse me. These react with amines to make ion pairs. So ion pairs are just 2 ions that counter each other. Typically one's negative, one's positive, that sort of thing. Okay, so what does that look like? Well, what I want you to do is when you think about an amine, which we could pick like the common amine that we like to use, this is ET3N or triethylamine. We use this in the Swern reaction. Amines are basic, and they're Bronsted basic. They're not as strong as like hydroxide. I mean, look at them, they're neutral. But the lone pair in the nitrogen is typically willing to pull off the hydrogen of something that's fairly acidic. And that'll work for acetic acid, even with just a pKa of 4. Okay, that's going to give our carboxylate plus this protonated amine. That amine has 3 ethyl groups around it. Now it has an H, and so the amine has got an H plus, or the amine is positively charged, and the carboxylate is still formally negatively charged. And so these things together form an ion or a salt pair. Now, this is called the ion pairs resulting from carboxylic acids reacting with amines are called ammonium carboxylates. Ammonium carboxylates. Ammonium means R3NH with a positive. So instead of an amine or ammonia, if we had NH3, this is ammonium. So just generally ammonium. Technically, ammonium is NH4 plus. And then a carboxylate is going to be the conjugate base of a carboxylic acid. We've used this term a few times in this lecture, but this is the negatively charged species that pairs up with the positive charge. Okay. Now, ammonium carboxylates are really important in biology because amino acids are readily form them. So they form ammonium carboxylates sort of within themselves. I don't want to say intramolecularly because that kind of implies that the reaction occurs intramolecularly. But what I want to say is this. All right, so an amino acid that we use to build all of the proteins in our body is called an amino acid because what we've done is we've put an alpha amino. Now, an amino is just an amine. Alpha amino carboxylic acid. Okay, so you can see we've got the alpha label that tells us that on that carboxylic acid at the alpha position, there's going to be an amine, which in this case has 2 hydrogens and 1 carbon attached to it. Okay, so this is just some amine. The R group is what changes between all of the amino acids, and that forms the alphabet that we need to make our our proteins and that sort of thing. But that's a tale for a different day. Okay, so what this will do is this will transfer proton. So this will kind of move an H plus, and it'll move the H plus that's on the carboxylate. That's what's going to transfer. And it's going to transfer so that it lands somewhere else on the molecule. And it's going to land on the amine. So here's our ammonium carboxylate. Okay, so amino acids readily form structures with an ammonium and a carboxylate. This is important to note because what we have here is we have an overall neutral molecule with a permanent separation of charge. What do I mean by a permanent separation of charge? Well, what I mean is we've got charges present, specifically a positive and a negative, okay, that counter each other. So that's a separation of charge. We've seen that all the time in resonance structures, right? As soon as we push arrows off a carbonyl, we get to a resonance structure with a separation of charge. Here's the thing, that's not necessarily a permanent separation of charge. That's just a different depiction of a molecule. In the structure I have shown above, after the H plus is sort of moved over, we have a permanent separation of charge. If we want to get rid of the charge, we have to actually transfer the proton back. And certainly there's an equilibrium for that, but that's a chemical reaction, okay? In terms of depicting the molecule, I cannot depict this in a way where I don't have a separation of charge. I can't neutralize that those charges, okay, I just can't neutralize them. They're sort of forced. Now that's got a special name. If you have these two properties, overall neutral molecule with a permanent separation of charge, this is classified as a Zwitter-ion. It's German, so I like to put the V on the W. So Zwitter-ion, but Zwitter-ion is fine, whatever. Okay, so these are molecules with a permanent jeepers. Okay, give me a second here. Let's spell permanent without rushing. So all 20 amino acids exist as Zwitter-ions in the conditions that we usually see them exposed to, which is some sort of aqueous medium. Now, what's great about that is this improves their solubility in water. It improves the solubility of amino acids in water. So it's a really nice trick by biology, because I mean, amino acids, if I scroll back up my notes, we could see are very organic. They've got carbons and stuff, and then they've got, they're much more carbony than oxygeny. So sugars can dissolve. Sugars can dissolve in water using all of the hydroxyl groups to hydrogen bond. Fats choose not to dissolve in water for the most part, and that's kind of their functional responsibility. But amino acids we really need to dissolve so that we can build proteins that stand a chance of also dissolving. The way that amino acids get to dissolve isn't just a huge abundance of OH groups like we see with carbohydrates. Rather, it is the presence of Zwitter-ionic character in the amino acids, which that charged state really can facilitate. That salty state, I guess you could think about it, really facilitates dissolving in water. Now, it's not easy for some of them. Some amino acids have side chains that are too carbony, or what we call greasy, and they can't get into solution, which as effectively as things like glycine, for example, which has that R group would be just a hydrogen. So anyway, some interesting features about some carboxylic acids with amines built in, but an important reaction to note: carboxylic acid and amine will make an ammonium carboxylate. As for now, I think it's appropriate just to kind of cut this off, and we'll look at the reaction of carboxylic acids with stronger acids in the next lecture, and that'll get into a cool reaction called the Fischer esterification. Okay, so until then, I'll see you next time.